This video is about the very important theorem of Lagrange, the Lagrange's theorem. I put here order of h divide order of g because there are so many Lagrange's theorem that sometimes it's hard to say which one it is. Okay, this is the Lagrange's theorem on group theory. So the theorem says if G is a finite group and H a subgroup of G, then the order of H divides the order of G. So let H be a subgroup of G, the order of H divides the order of G. More, the number of distinct left cosets, left or right cosets of H in G is the index of H, the index of H in G, or this means the index of H in G, meaning the number of distinct left or right cosets, meaning of course order of G, order of H. So the index, the number of left cosets H in G will be the order of G dividing the order of H. Okay, I'm going to show you a first proof, a very simple one. Proof. Okay, let us take some left cosets like A1H, A2H, AN, or I'm going to call it R, ARH. So these are the distinct left cosets of H in G. So for any element A in G, we will have AH equal AIH. So there will be one I, right? If it is not 1, it will be 2. If it is not 2, it will be 3. So there will be a moment where an element in G, the left coset of A in H, left coset of H. So with the operation A operation subgroup will be equal to AIH. Do not forget we are working in finite groups, okay? And of course we saw that in previous videos, A, the element, have to be in AH. I think this was one of the properties we saw the last video. Okay, properties of left cosets. So, well, it was the first property of left cosets. A is always in AH. Okay. So, for each member of G, any member of G will belong to one of the cosets AIH, right? So G is going to be A1H union A2H union till the last one, right? ARH. Okay, Okay. Okay, but we saw in the previous video, in those properties of cosets, that AH intersection BH equals the null set. Okay, so this being true, these sets will all be disjoint. So the order of G is going to be equal, since they are disjoint, the order of A1H plus A2H plus etc. till ANH. So the order of G will be the sum of the orders of all the left cosets. Okay, but what is AIH, the order of all A's? Well, it will be equal to the order of H, because each single one, that's another property, right? We saw in the previous video. Each single, all the left cosets will have the same order as the subgroup. Okay, so the order of G will be R orders of H, right? R, it will be 1, 2 till R. So it will be, since it will be, we will be adding the order of each one, so G, the order of G will be equal to R order of H. Okay, so the order of G, the order of H will divide the order of G. You will get R here, and this proves the theorem. So in quick words, we would say that okay, we want to prove that the order of G divides the order of H divides the order of G, right? So first we built the cosets A1H, A2H, ARH, right? But we saw in previous videos that cosets are equivalent. So any left coset will have the same number of elements as H. Any left cosets will have the same order as H. So all these left cosets have order H. They all have the same order. We saw that in previous videos. Okay. So, but since left cosets are identical, they are either identical or disjoint. Okay, so each element of G, each A in G, belongs exactly to one left coset. So we pick A, and A will be either here or here or here. Okay, A will belong to one of these, not to one, it will belong, A will belong exactly to one left coset. Okay, so from the definition of index of a group here, well, we can write it this way. So the order of G is going to be equal to the order of H, right? This was supposed to be R, right? Yes, I think I changed it, right? Yes, I changed it to R. So the order of G will be equal to the order of H, R times, okay, R times. Okay, so the order of G dividing the order of H dividing the order of G, you get R, a natural number. Okay, so now I want to leave here 4 quick corollaries. Corollary number 1, the order of A divides the order of G. Of course, for all A in G. So in a finite group, the order of each element of the group divides the order of the group. The proof is really simple. Do not forget that the order of an element is the order of the subgroup. So the subgroup generated by that element, so the order of A will be equal to the order of the subgroup generated by A, so that will be equal to the order of a, let's call it H. Let's call H the subgroup generated by A. So this is the Lagrange theorem, right? With the subgroup, because the Lagrange theorem says if G is a finite group and H is a subgroup of G, then the order of H divides the order of G. Okay, so proved. Second corollary, groups of prime order are cyclic. A group of prime order is cyclic. So let us say that the order of G is P, a prime number, okay, a prime order. Let us pick A in G, and of course I don't want A to be the identity. So A will generate a subgroup, right? What is the order of this subgroup? Well, the order of this subgroup will divide the order of G, right? And the order of this subgroup will be different from 1. Okay, so if the order of the subgroup is different from 1 and divides G, and G is prime order, the only possibility here is the order of A to be equal to the order of G. And this proves the corollary. Groups of prime order are cyclic. A group of prime order is cyclic. It has to be a cyclic group, right? Okay. Corollary 3. A to the power of the order of G equals the identity. Let G be a finite group and let A be an element in G. Then A to the power of the order of G will be equal to the identity. Well, it's really simple. Taking corollary number 1, the order of any element will divide the order of G, right? So, proof. The order of G will be equal to, so the order of A will divide the order of G. So let us say we get K. Okay, so the order of G will be equal to K order of A, right? Okay, let us take now these two powers. So A to the power of H equals A to the power of K A, right? Okay, but what is a to the power of k a? That will be the a to the power of a, that's the identity, right? To the power of k. What is the identity to the power of k? That's the identity. So a of the power of g will be equal to the identity, and that proves the theorem. The theorem, not the corollary, right? That a to the power of g equals the identity. Okay, last one. Fermat's, the so-called little theorem of Fermat. For every integer a and every prime p, a, the integer to the power of p, module p equals a module p. Okay, the proof is relatively simple. We take again the division algorithm. We are going to say that a equals pm plus r. Okay? So r has to be a positive number and of course less than p. Okay? So a equals r module p, right? So all we need now, we need to prove that r to the power of p equals r module p. Okay? Okay, first case. Imagine r is 0. Well, the result is trivial, right? Because r is in the group of units of p, right? Okay. Now, sorry, this is 2. So, if r equals 0, this is trivial, right? 0 to the power of p will be 0, and 0 module p will be 0, so the result is trivial. Okay, so I jumped here. So this is my second case. I have to assume that r is in the units module p. Okay, do not forget that units module p will be 1, 2, and p minus 1. Okay, of course this is multiplication module p. I insist in writing module p. Okay, that's the units module p. Okay, but since r is in units module p, we said in the previous corollary that a power to the order of g equals the identity, right? So r here, r to the power of p, it will be r to the power of the order of the group. The order will be here p minus 1, the units module p, and that will be equal to r to the power of 1, right? Okay. Sorry, r to the power, no, I have to write it correctly. Wait a sec. Okay, r to the power of p equal r. So r to the power of p minus 1 equal 1, right? So r to the power of p has to be 1, and that proves the corollary. Okay, that's the famous Fermat little theorem. For every integer a and every prime p, a to the power of p module p equals a module p. We use this a lot in current calculations.